A very warm welcome in the course of numerical methods. We are in the module of solution of system of linear equations. Already we have discussed few methods and we have already discussed some methods under direct method. Today in this topic we are going to discuss the iterative method for solving the system of linear equations. And there are numerous methods on this particular sub criteria. We are going to emphasize on Gauss-Seidal method. So already we have the concept of general representation. If I just restrict myself into 3 cross 3 system, so it will be a11x1, then a12x2, a13x3 is equal to b1, a21x1, a22x2 plus a23x3 is equal to b2, a31x1 plus a32x2 plus a33x3 is equal to b3. Now we are going to introduce some condition on this particular system. As of now, we are giving you it as an information, but there are some certain proofs of these conditions. Here, you please see that a11, a22, a33 are diagonal elements. Okay. Now, if we have one condition that aii is greater than summation of mod of aij, where I runs from 1 to n if there are a number of variables n, so it will be here 3, and I not equal to j. That means if I consider the system in such a manner that the principal diagonal element itself with its modulus, that means from its magnitude, is greater than the summation of the remaining coefficients modulus. So the first line we can write it as a11 is greater than a12 plus a13. In the similar manner, a22 is greater than a21 plus a23, and a33 is greater than a31 plus a32. If it happens, we call that system as diagonally dominant system. And if a system is diagonally dominant, then the method what we are going to state now will be convergent. That means you will get the values of x1, x2 and x3 by following this process. It is guaranteed. Now one can say that if a system is diagonally dominant, we can check it. But if a system is not a diagonally dominant system, what we can do? So in those types of systems, we can have two classifications. One, we can convert it into diagonally dominant one, and the next one if we can't. But how we are able to convert in those cases which is convertible? Look at this. If I interchange in a system of linear equations, suppose there are two equations in a system of linear equations, if I interchange them, that means if I write the equation number 2 first and the equation number 1 in second, then also the solution remains same. In both the cases, solution remains same. But the condition of diagonally dominant system may not be existing in the first representation, but it may be in the second representation. So we can try this process if the given system is not a diagonally dominant system. Now, one question should be there in our mind, that what we are going to do with that. So just for example, if I am writing it as, suppose 2x1 plus 3y1, 2x plus 3y plus 4z is equal to 9 or 7, whatever, I am just for example, and 10x plus y plus z is equal to 14. Now from the first equation also we can write x is equal to 7 minus 3y minus 4z 1 by 2, and from the second equation also we can write x is equal to 14 minus y minus z into 1 by 10. So if there are n number of equations, we can write x in n types. This diagonally dominant system gives us the clue that if it is diagonally dominant, then write the expression of x from that equation only where the coefficient of x is dominant. So obviously you are not going to get more than one equation in a diagonally dominant system where the coefficient of x is dominant. You will get only one in a system if it is diagonally dominant, and then you got the equation from where you have to write x. So obviously in this case we are going to write x from the second equation. So there is no question of accepting the first one in the further studies. Where the further studies will be performed, I will show you just after 1 or 2 minutes. So I just want to emphasize that why we are going to write it in diagonally dominant system. And next, though we are going to discuss Gauss-Seidal method, but Gauss-Seidal method is based on Gauss-Jacobi method. As Gauss-Seidal method is having faster convergence than Gauss-Jacobi, that is why we use Gauss-Seidal method. But only one thing I want to mention about Gauss-Jacobi method, that is in n plus 1th step, we all use the information from nth step. It is the concept of Gauss-Jacobi method, and we are updating, or rather we can say we are upgrading this concept, and we get Gauss-Seidal method. So now how we are upgrading that, I will show you. So let us take one system of linear equations, very simple system. 10x plus 2y plus 4z is equal to 16. X plus 10y plus 3z is equal to 14, and 2x plus 5y plus 10z is equal to 17. So obviously it is very much clear to us that the given system is a diagonally dominant one, because we can see it that mod of 10 is greater than mod of 2 plus mod of 4 in the first equation. In the second equation also, the coefficient of y, that is the second diagonal element, is greater than 1 plus 3, and similarly for the third one also, that is 10 is greater than 5 plus 2. So we are having it a diagonally dominant system, means now I will represent x in terms of the first equation, y from the second equation, and z from the third equation. So what I am writing, x is equal to 1 by 10, 16 minus 2y minus 4z, y is equal to 1 by 10, 14 minus x minus 3z, and z is equal to 1 by 10, 17 minus 2x minus 5y. Here concentrate on one thing, that as it is my iterative method, there is my initial approximation. Why initial approximation is required? Because initial approximation, it is denoted at x0, y0, z0, means we have not done any calculation at the 0th step. We are assuming their values, because if I construct the schematic form of this working rule, basically it is n plus 1, and now please construct this form with the consideration that when we are at n plus 1th position of x, we have the nth position of y and the nth position of z. But when we are trying to calculate the n plus 1th position of y, I have nth position of x, nth position of z, as well as n plus 1th position of x also, because already I have calculated x n plus 1. So in case of Gauss-Jacobi method, it will be only xn, and in case of Gauss-Seidal method, as it is upgraded one, and we already have xn plus 1 calculated by us, so it will be xn plus 1, but in case of z it will be n, because zn plus 1 is not known to us. If this logic is clear to you, then immediately you can decide that when we are going to calculate zn plus 1, as xn plus 1 is known to us, we will use here xn plus 1, as well as in case of y, already yn plus 1 is also calculated in the previous step, so we will use here yn plus 1. So this is the structure of Gauss-Seidal method. Now only one thing is remaining, that using the initial approximation we have to find out the values, and as it is iterative method, it may be mentioned in the question, or it may be required, the number of steps are mentioned, suppose perform 4 steps, or sometimes it is mentioned that up to 3 decimal places. According to the requirement of the problem, we will proceed for the calculation. So before starting the calculation, we just have one more query, that what is initial approximation. If it is given, okay, I have to take that one, and if it is not given, I can take it as per my choice. I can take them same, I can take them different. So suppose for this problem we are assuming that they are same and they are 0. So what will be the value of x1? So it will be 1 by 10, then 16 minus 2 into y0, that is 0, then 4 into z0, that is 0, so we get it as 1.6. Now we will go for the next case, that is putting n equal to 0 in the next line. We get y1 is equal to 1 by 10, then 14 minus x n plus 1, that is x1. Already x1 is calculated, so it will be 1.6, then minus 3z0, that is 0. So 14 minus 1.6, we will get 12.4 divided by 10, that is 1.24. And similarly, we are going to put z1, means n equal to 0, we get z1. And from this structure, we get 1 by 10, 17 minus 2 into x, that is 2 into 1.6, that is 3.2, minus 5 into y, that is 5 into 1.24, that is 6.2, and simplifying it, we get it as 0.76. So this is nothing but my first iteration. So it is nothing but the first iteration. In this way, second iteration will be performed, third iteration will be performed, and consecutively, according to the requirement of the problem, we will perform the number of steps, or we will check whether the correctness is achieved at least up to 3 decimal places. So for our own benefit, we do these particular calculations in our technique of using calculators or something like that, but it will be better for us if we can represent it in the tabular form. So now we are going to construct one table which will help us to proceed, as well as which will help us to make the person who is going to see our effort, it will be also very much easy for him or her to understand. So we will do the calculation for x, the calculation for y, and the calculation for z, and it will be n. So it will be x n, it will be y n, and it will be z n. Obviously all of you are able to understand that here n is written in the first bracket. That means here I am talking about n means the iteration, it is not the power. So when n is 0, that is 0th iteration, that means our approximation, initial approximation, x0, y0, z0. And when n is 1, you can check that we get already x1, which is 1.6, and then y1, that is 1.24, and then z1, that is 0.76. In the next case, when you are trying to find out n equal to 2, putting, please check, this 1.6 is coming using 0 and 0, but this 1.24 is coming after using 1.6 and this 0. Look at this 1.6 and this 0. Here it is 0, 0, and this 0.76 is coming when we are using 1.6 and 1.24, like this. So if we calculate for the next case, we will get it as 1.048. Please complete this calculation, what I am writing in the tabular form, by your own initiative. Then 1.0672, and it is 0.9568. And if we proceed further for one more step, we will get it as 1.0038. The next one is 1.0125, and the next one is 0.9925. Now I think already you have observed that after one or two steps you will get something like here, which is very close to 1, which is something like here, which is very close to 1, and obviously which is something like that will be very close to 1. Now I just want to share one information with you, that though you are going to get it very close to 1, but as you are not finding out direct method, whatever the value you are going to get, please try to write that value in place of x, y and z consecutively. And if you want to get it similar to 1, then don't write it equal to 1. You please write it is very close to 1, because you don't get 1, you get a number which is very close to 1. And just what I was saying just some time before, that this 1.6 is coming from these two calculations, but this 1.424 is coming from these two informations, and this 0.76 is coming using these two informations, and so on. So one more thing before completing this discussion, that you can see that the closeness to the exact value is coming faster in z than y than x, because you can see that z is using, from this calculational point of view, both the updated values, where y is using one updated, one previous, and x is using both the previous values. So it is one observation. And one more observation I can share with you. It is not mandatory that always you have to write this structure in this form. If you write the structure in the reverse manner, means if you write z, you are calculating first, then you can use z as 17 minus 2x n minus 5yn. In that case, the next thing what you are going to find out, suppose after z you are trying to find out y, then y will have zn plus 1 and only xn, and then if you are calculating x, then x will have zn plus 1 yn plus 1, and in that case you will see that the closeness of the value of x will be more than the closeness of the value of y and z. But ultimately, after a certain number of performance, you will see that you are going to get a very close value to the exact answer, because you are putting the value of third iteration only in these three equations. You will get the values are very close to 16, 14 and 17. That means they are going to provide you a very less error. The error is almost approaching to 0, which is not going to be the case for Gauss-Jacobi. Within this number of intervals, Gauss-Seidel will require a very less number of intervals than Gauss-Jacobi. So this is the thing for today. Finally, I want to share that these references you should follow for your further reading, and also please solve this problem according to Gauss-Seidel iterative method. So thank you all. Happy listening, happy learning.